So today, me and my colleague Martin will present to you which SRE principles we have adopted at Booking.com in order to run databases efficiently at scale. So today's journey, first we're going to talk about database reliability and how we perceive it at Booking.com. Then we're going to give you some good advice on how to choose your SLIs to define SLOs for your distributed database system. Next, we're going to deep dive into how we automated capacity planning for our MySQL clusters. And finally, we're going to discuss how we handle failures and how we embrace a post-mortem culture across the company. So at Booking.com, we operate at scale. And we operate at the intersection of technology and travel. We have chosen MySQL as our main relational data store. And we run multi-cloud and multi-region. This means that our fleet spans across bare metal, private cloud, and public cloud servers, and that we typically deploy in multiple regions. Typically, this is 3 regions in Europe. We have hundreds of clusters powering tens of thousands of servers. And an important thing to note here is that we do own the infrastructure for databases, but we do not own data or tables or schemas inside databases. So this is how a typical MySQL cluster looks like. So whenever in this talk you hear something about MySQL cluster, this is something that you can picture. We have a single primary for writes. We have a second layer of intermediate primaries. These are standbys that take load off the primary, mostly for replication purposes. They are distributed across regions. And then on the third layer, we have read-only replicas. We follow a scale-out architecture for reads because our workload is mostly read-heavy. And those replicas replicate from the intermediate ones. Next up, let's briefly discuss the database reliability engineering term. When I joined Booking.com, I wasn't even aware of this term, DBRE. So it's a sibling term to SRE, which you're probably most familiar with. We define this as a set of tools and practices around database systems in order for them to run reliably, scalably, and in compliance with regulations. Our database engineering team consists of both SREs and DBAs. So we do require expertise in database operations, and we try hard to provide self-service tools for developers. In addition, we participate in on-call rotation, so we do cooperate with peer SREs from other teams and join firefighting calls when an outage happens. Finally, we try hard to deliver database observability. This means that we do care about understanding our systems better, know their health, and measure their performance. And then let's see which SRE principles we're going to talk about today. First one is monitoring distributed systems. A database that runs across clouds and locations, and a database that has members that are different by nature, primaries and replicas. Then, operating a database at scale comes with repetitive operational tasks that are mostly common across clusters. This means that we aim for automation. And finally, embracing a post-mortem culture is very important because outages will happen in production inevitably. So first topic, let's talk about SLIs and SLOs for distributed database systems. These come from experience, like the real world. We have seen bad examples of using a database from developers. So measuring the database, the performance of the database is not always easy. Actually, it's kind of tricky. We see full table scans, non-index complex queries that are slow, or users abusing a database as a queue. These are problems that we need to solve, and they might give you a false positive that your database server is misbehaving or underperforming, while it's actually healthy and performant. So in this slide, we see 3 SLIs that we have previously used for our SLOs, and they didn't quite work for us. So the 4 golden signals, latency, traffic, errors, and saturation, is usually a good starting point. But for us, for databases, they do not always work. So query latency is something that we saw that was quickly violated because a complex query without indexes will be slow. Overloading, going to throughput, overloading a primary with read queries will make it slow for writes. And finally, regarding replication delay, if you have a developer that does a bulk operation like an update or a delete, this will inevitably introduce replication delay in your replication chain. So if you cannot measure it correctly, you cannot actually improve it. And Martin will tell you about how we chose our SLIs for SLOs for our database systems.
Thanks, Ioannis. Hey, hello, everybody. So, well, we know that we have rejected these 3 SLI for our databases SLOs. So let's talk about what we are trying to do. The first thing is we need to decide where to measure, right? For our customer, probably measuring the InnoDB buffer pool pages or CPU total makes no sense. So it's not going to tell us anything. So we need to go to the right level of abstraction or in the chain. So that's why we decided to go with these 3 SLIs. The read availability, which basically is about our read replicas can reply to requests from our services for read data. Write availability, which is about the primary of our topology is able to write into our databases. And replication running, which basically means that the replicas, the 3 layers, are replicating correctly. But we don't measure the delay of that replication because we cannot control it. And that's quite important. So let's go into the read availability SLO we provide. At Booking, we provide 4 nines. Basically, we do the collection of this SLI by a particular component called MySQL Availability Reporter, written in Golang. We basically take a point every 10 seconds, a measurement, from 2 different read replicas. We execute a select statement, a select query in the database. If at least one of those assists, for our purpose, it's on OK, otherwise a miss. And then we do the calculation that the ratio of OK divided the total of points. Then you can see our metrics. For write availability, we have something quite similar, with the difference that the target is a little bit lower. We have 3 nines, 7. That's because we have only a single primary in our clusters. So we don't have redundancy for the primary. We will do switchover, failover more often, so we cannot offer the same. But how we measure or how we collect the data is quite similar. The same component, the MySQL Availability Reporter, execute an insert query into the primary. So basically, we have a table that we insert. We call it the heartbeats. And if that insert success, it's an OK. If it fails, it's a miss. Same as before, OK divided the total of metric, give us our SLO. In this picture, you can probably see, or I want you to see, this MySQL Availability Reporter, the architecture. It's written in Golang. It's in-house. It runs in Kubernetes. Basically, in all our region, we have a Kubernetes cluster where we deploy this component, MySQL Availability Reporter. It takes reads from the read replicas. It measures the reads in the read replicas, and it measures the write availability from the primary. If you take a look at the lower part, you will see that we have a service, the same service deployed in 2 regions. So the service looks for read replicas in the same region, always. That's all our services at Booking do that. But for primary, they need to go cross-region because we have 1 region. So for the primary, we always have cross-regional traffic. Our MySQL Availability Reporter follow the same application behavior. It crosses the region to go and do the write. And this is important because basically we can measure the pain that our customers are having. Now let's go into replication running SLO. The target is 99.95, a little bit lower because we cannot control the network. There are more things that can go wrong. So basically, we cannot offer more than that. The difference is like we don't measure it with the MySQL Availability Reporter, but we have a different component. We call it admin agent. It's written in Python. It's part of our fleet management infrastructure component. And it runs inside the MySQL server. In the same places where we have a MySQL server, we deploy this, you can imagine, as a sidecar. And it basically, periodically, every 10 seconds, it's query the performance schema of MySQL. That's a particular schema where you can get performance information. We particularly ask about the replication. Is running or not? If the replication is running, it's OK. Otherwise, a miss. Same as before. OK divided the total, give us the SLO. This is the architecture of, again, 3-layer primary, intermediate primary, and read replicas. In all the servers, we have MySQL and admin agent, which is written in Python. 10 years ago it was started, or more or less, but it's actively under active development, so that's good. And it periodically, it's connected to the database. It asks for the replication running through the performance schema of MySQL, and then send the data back to, in our case, we have Graphite and Prometheus. For this case, we use Graphite. But now, let's go and see real numbers from Booking.com. Probably if you know Booking.com, you have heard about Genius program, Genius level, or whatever. This is the Genius cluster, the SLOs of the Genius cluster for 1 month. That's 30 days. We have read availability, write availability, and replication running. In 3 cases, this is a really good month. We are above the target. The target is the yellow line in 3 cases. Something interesting to see. Even if we have drops, we are not breaching our SLO. And that's totally fine. We are consuming our error budget, but we are not breaching the contract that we have with our customers. But not all the cases are happy. This graph shows all the root causes that we have for breaching our SLO. There are a lot of more, but this is a summary. I want you to see particularly this one, which is the orange one, which is the bigger one in all the cases. And it's about user-induced behavior. User-induced means a service using wrong MySQL. It means that we have a lot of work to do in our teams to improve this. There's room for improvement. We can do a lot of protection or measurement on top of MySQL over fleet to reduce this number. But something that is key and is important in the SRE culture is to educate our developers. We have an important role here, or a really important opportunity to go and help them to use our fleet better, or we can understand how they are using and why they are using that way. So my takeaways for you in this section is, of course, choose SLIs that you can control. If you cannot control your SLI, probably it's not a good candidate for your SLO, because it's going to give you false positives, alert fatigue, and more. Decide the correct place to take the measurements. Most of the time, going closer to the customer is the right thing to do, but it's not true for all the cases. In our case, replication running is not something we can measure from the user, but we need to measure from the server, and that's totally fine. So don't stick to the rule of always close to the customer. Yes, when it makes sense. And then, what is, at this point, it should be like a super well-known rule. Don't look for 100% reliability. It's not worth it, and it's super expensive in terms of engineering effort, probably money, and everything. So please embrace the risk. Moving on. Now let's move into automation, MySQL capacity planning. So how we do automation? Databases, by nature, introduce a lot of toil, You can imagine we need to provision servers, configure MySQL. Depending if they are replica or a primary, they have different configuration. We need to do switchover, maintenance, failovers, MySQL upgrades in the whole fleet, and so on, and so on, and so on. So we cannot do it without automation. So for that, we rely 100% on automation. If we can automate it, we need to do it. Because remember the scale. We have more than 10K servers running MySQL, and we have only 20 SRE DBAs to handle that fleet. So basically, the fleet grows faster than the SREs. So we need automation. And now going back to Ioannis, who is going to go deeper into capacity planning.
Yeah, thanks. So let's deep dive into how we automated MySQL capacity planning. We see this as a very important DBA task to keep the lights on. KTLO, we call it inside the company. So first of all, it's about risk mitigation, right? So you want to ensure that your database is capable of handling traffic, and especially during peak loads, say summer or Christmas. Then it's about cost control. We do not want to see oversized MySQL clusters, because these obviously increase our bill, especially when moving to the cloud. Then it's about scalability. Automating a time-consuming task that is repetitive and common for all MySQL clusters is important, because as Martin said, as the number of MySQL cluster grows and as our business grows, we cannot afford to run things manually. Then we saw this as a continuous learning exercise because it helped us understand our systems better, do profiling, understand the correlation between hardware profiles and workloads. So it was really good to learn about all this stuff while implementing automation for capacity planning. And finally, we can use it for analytics. So the data that come up from capacity planning can be used to debate between vertical and horizontal scaling, do forecasting, and reporting. So here are some design decisions that we took before we started implementing our automation. First of all, we wanted to run this daily during peak hour. This is around noon. Then the second thing was that we wanted to run this against our production fleet. This is not very common, so we took the risk, but we had the confidence to do this. So we do try to capacity test production servers serving real traffic. Of course, to do this, we had, going to the third design decision, we had to introduce a kill switch, right? So whenever an incident happens or whenever we had to block rollouts, it was very important to have a kill switch to stop the capacity test at any time. Finally, maybe the most important decision of those was to prioritize business continuity over cost efficiency. This means that our first priority is not to reduce costs. This is always in our heads. But first, we want to ensure that traffic can be served. So this is the building block based on which automated capacity planning was built on. So this is MySQL pools. A MySQL pool is a logical definition of read-only replicas that exist in every cluster that serve specific workloads from specific services. This is very helpful to isolate between services, separate concerns, and solve the noisy neighbor problems inside MySQL servers. As you can see in this graph, a pool has multiple pool instances. This is a very typical setup of ours. So a pool spans across 3 different regions. In this example, London, Amsterdam, and Frankfurt. And each pool instance has multiple pool members for redundancy. So we typically have at least 3 pool members in every region. Let's also note here that not all pools are defined in the same way, but this is kind of a typical setup of ours. So then we had to introduce some metrics that are related to capacity. For this, we use MySQL exporter, which is a Prometheus project. Actually, we use a fork of this, and we have done some internal implementation on top of it that we probably plan to contribute upstream. The 3 metrics that we care about are the number of select statements performed by a MySQL server, and we take the I rate of it over the last 2 minutes. Then we care about the threads connected, which is the number of threads or clients that are connected to a MySQL server. And finally, we do care about the threads running. These are the MySQL connections or clients that are actually running a query right now. We do measure those 24/7. So we have a Prometheus server scraping the MySQL Prometheus exporter, which runs next to MySQL boxes. So let's see this as a pipeline. So this is our automated MySQL capacity planning in phases. So first, we have the test phase. In this phase, we try to saturate boxes by routing production traffic to specific MySQL servers. So the primary of each cluster randomly selects a MySQL replica in each one of the 3 regions and schedule a capacity or stress test. Then the selected pool replica runs the capacity test either until a termination condition is met, which means either when saturation was detected in the box or when the maximum number of trials was reached. Then, once the capacity test finishes, the pool replica that was selected to run the capacity test pushes threshold values for the 3 metrics that we saw before and store them in Graphite. And this indicates the maximum load or capacity this MySQL replica is expected to take. Next up, we enter the calculate phase. In the calculate phase, we spawn a cron job. We do have dedicated infrastructure for running cron jobs, which reads the capacity metrics and the threshold pushed by the previous steps. And it does some heuristics to calculate the new or the desired target sizes, both for regional pools and globally for the whole pool. We'll see this in more detail right after. And finally, we have the scale phase when another cron job starts at a different schedule. This cron job reads the results from the previous phase, which is the target sizes. And this is responsible for speaking with our internal provisioning API, which abstracts all three platforms that we run on, bare metal, private cloud, and public cloud, and automatically grows or shrinks pools as needed. Here we can see that the way we manage to direct traffic into boxes is by modifying weights. So we do have implemented a service discovery mechanism, which allows us to route traffic to specific boxes. So we do some iterations, and in each iteration, we increase the weight of a specific MySQL replica. And the bigger the weight, the more traffic gets directed to the box. So this is a repeated procedure until max trial is reached or saturation is also detected. How do we detect saturation? We look at three metrics, which are CPU utilization, disk read latency, and the maximum numbers of MySQL connections. And then let's talk a bit about how we calculate the target sizes, the desired state for our MySQL pools. First of all, we calculate the regional target size, the target size of each pool instance running in a specific region. This is calculated as a division between the P90 value of the capacity metric in the last 24 hours, which is emitted by the MySQL exporter, and we divide this by the median of the same metric over the last week. We divide this by the threshold pushed by the capacity metric over the last week. This division gives us an indication of how big or small this pool should be. We do this for all three metrics, and we keep the maximum target size calculated for all these three indicators. And finally, we stick to some empirical upper and lower thresholds, so we need to ensure that we are within specific bounds so that we do not over-provision or under-provision pools. We do not like drastic changes. We want it to go gradually. Once we have three, for example, regional target sizes in three different regions, we go and calculate the global target size. So even if we might have three different numbers, we will calculate a single number for the whole pool, and we will apply this number for all regions. So this is an approach that is rather conservative and leans towards over-provisioning, but we do want this because our design decision was to prioritize business continuity over cost efficiency. So we take the sum of the three regional target sizes, and we divide it by 2, n-1. And this gives us some spare room, some extra space, in case a region goes down. On top of that, we do some extra adjustments, which are meet the minimum target size requirements for specific pools. So there are MySQL clusters that are very critical for production. For those, we do need to meet some minimum standards, and we want to fail safe in case something goes wrong in our calculations. On top of that, we do add some static numbers, some extra number of servers, to budget for random hardware failures or maintenance or security patching, and so on and so forth. In a very simple example that we have been seeing, we have three regions, and assuming that we have calculated regional target sizes of 5, 5, and 2, which the total is 12, we divide by 2 instead of 3. So we end up with 6 replicas instead of 4. So this allows us to afford a regional failure because each MySQL pool instance can serve 1.5 times the traffic it normally serves. So let's see this in action with an architectural diagram. This is the test phase that we saw before, and we start where the Prometheus server scrapes MySQL exporter in individual pool members in 3 regions. So we get the values of the capacity metrics, and at some point, the capacity test is scheduled by the primary of the cluster in a random replica in each one of the 3 regions. The selected pool member in each region runs the capacity test until a termination condition is met. And once done, it pushes the threshold values indicating maximum capacity to Graphite. We do this daily. Then we enter the calculate phase we talked about before. So we spawn a cron job. The cron job reads the P90 values for the past day from Prometheus, and also calculates the median of the threshold values over the past week from Graphite. It does this heuristic about regional and global target sizes, and finally pushes back the new desired state to graphite. At the last step, we enter the scale phase, so another cron job is scheduled. It reads target sizes from the previous step, does some extra calculation, which is about calculating the diff. This is the current capacity vs the desired one. And depending on the result, it grows or shrinks pools by calling our provisioning manager. This abstracts all APIs that are, for example, AWS EC2, bare metal, and OpenStack. And finally, we do the actual scaling of the pools. So you can see that in this example, the number of pool members was increased from 3 to 4 in all 3 regions. This is also a real Grafana dashboard from our fleet, which shows that capacity indeed fluctuates with traffic. This is over 2 weeks. So you can see that it's around 6 and 10, or a bit more. So you can see actual MySQL pools getting scaled, or scaled up or scaled down, depending on the traffic. And another thing to note here is that our capacity tests are not 100% successful. This means that there are various reasons why these might fail. For example, we have seen errors with grants, with configuring the maximum number of user connections. We have seen errors with database logs or blocked rollouts. So these are common causes that prevent the capacity test from running. And depending on the business priority of each cluster, we require a minimum number of successful capacity tests within a given time window. And regarding future plans, because by no means this capacity planning mechanism is complete or perfect, we do want to explore new hardware profiles that become available in private and public cloud. As we move more and more servers to the cloud, we do want to fine-tune our capacity thresholds towards cost efficiency, because right now this is our second priority. Of course, we want to minimize errors, so we want to handle the errors that we see and are common in a good way. And finally, we consider using a single sync for metrics, because you see we use both Prometheus and Graphite right now. This would simplify the picture a bit. And with this, let me pass this back to Martin, who will talk about our postmortem culture.
Okay, thanks. It's nice to see that our capacity planning are not trying to reach 100%. Okay, system breaks, that's life. We know about this, right? Don't panic, but if I see that shark, probably I will panic. Try to stay calm, or stay calm, whatever. But yeah, the idea is, we all know, or hopefully I will share that, incident will happen. We cannot do anything about that, and the idea is to embrace failure and try to learn from that. So I want you to introduce you how we do it at Booking. We have our service health program, which consists of 5 initiatives, like the service health review. We have a weekly, or we embrace people's teams to do a weekly service health review to go over the SLOs, the failures, and also to celebrate success about the services. We have the incident management procedure, the standard how we do and how we manage incident at Booking. The roles defined in an incident, like incident commander, the communication leader, the firefighter, and how to react in those cases. We have postmortem, or RFOs, reason for outage, which is the continuous learning process. I really love, or I think that incidents are a really good or nice opportunity to learn and to share knowledge. Then we have drills, or network drills, where basically we have an exercise procedure several times per year, where basically we play with production. We isolate a network, we take down a region, and we see what happened with Booking.com. The idea is to learn and to improve the reliability of Booking.com as a whole, and try to fulfill with our mission. Then we have the business continuity part, which is more about automatic checks to ensure that services with certain criticality reach some standards, like they have capacity testing enabled, failovers, restore and backups enabled, and so on. Let's go into postmortem. Let's embrace the failure together. Postmortem are nice because we can learn more things about our services that we previously had. For example, we can discover new failing modes. We can discover ambiguity that we have when we design the services. We can discover dependencies that we didn't know about it. So we can learn a lot from incident and postmortem. We can understand, minimize, and try to remove failing modes. And also, the most important thing, in my opinion, is learning and continuous improvement. Learning is critical in this place because we can learn a lot from postmortems. Of course, we should do it in a blameless way, and if we do it in a blameless way, we can increment the transparency of the process because people will be able to speak loud. So these are, we call it RFOs and booking instead of postmortem. We do a lot of them, of course. These are 10 for MySQL in this year. We have to write them. But yeah, in order to have a postmortem culture, you need tooling to support it. We have what we call the RFOpedia, where basically you can search for postmortem in the whole company. You can create, you can search, you can edit, you can review the postmortems. Postmortem follow a template. So you have a lot of information like the owner of the postmortem, who wrote it, the team, the reviewers. Even here you can see the PagerDuty incident related to this particular postmortem. And also you have timeline of the event, context, business impact, and so on. But one of the most important things, in my opinion, is the follow-ups. Because the follow-ups are going to drive the improvements for those particular services. What needs to be done to improve? And we have follow-ups in 2 categories, high and low priority. High priority are those that we have internal policy to complete those follow-ups in 7 days after the incident. That's the idea. If you have a high priority follow-up, you need to do it. It's your priority for reliability. And if a low priority, you can probably slack off a little bit because probably that's something you need to research or improve or whatever, but it's not critical for this particular incident. Sometimes follow-ups are a contribution to open source. Here I have a contribution to MySQL itself. After an incident, I contribute to MySQL. Ioannis contributed to MySQL shell after an incident as well, so that's good. When we have time, resources, we go and contribute. I think that's good. Okay, but the message I want to transmit is like, it's not about writing a document because you are checking a mark in your procedure for incident. It's about a culture around postmortems. We will have incidents always. We need to mitigate those incidents. Then we calm down and review and try to analyze the root causes of the incident, write the RFOs, review the RFOs, and eventually publish the RFO to make it available for the whole community. In our case, a booking. Then more review will happen, but that's not the end of the story. On top of that, at booking, we have what we call the RFO book club, where we meet to read RFOs, super fun. And we have the RFO company annual review, where the SRE community at booking also meet to review RFOs. But that's a really good exercise to learn about the whole company. We discover patterns, we discover failing modes, we discover that a lot of services are having the same problem or issue. Or we discover that team A is solving an issue, but team B is having that issue after 2 years because they are not talking to each other. So these initiatives are shaping the culture of postmortem rather than filling the mark in a procedure. And I think that's super worth it. And that's it, all we have. So we are open for questions.